Welcome to the United States Sports Academy, America's Sports University. This is Unit 9 of Math 465, Statistical Measurements in Sports. This unit covers non-parametric statistical techniques. It is important to note that this presentation is simply a summary of the topics covered in Unit 9 and not intended to replace the textbook or any supplemental readings.
Welcome to Unit 9 of Statistical Measurements in Sports. In this unit, you'll learn about non-parametric statistical techniques. Now, some of the tests that you'll learn about in this unit will be similar to some of the tests that you've previously learned about in this course, only this time they're non-parametric tests. In other words, the assumptions of normality have not been met. Non-parametric tests are usually run on ordinal and nominal data. Now, the main things that you need to learn in this unit are, number one, being able to distinguish between non-parametric and parametric tests. And two, you want to be able to identify and understand when it is appropriate to run non-parametric tests. If you have any questions, please contact your instructor. Thank you.
After successfully completing this unit, you should be able to understand and use non-parametric statistical techniques such as chi-square, rank-order correlation, Mann-Whitney U-test, Kruskal-Wallis ANOVA, Friedman's two-way ANOVA. When data are of the nominal or ordinal type, the assumptions of normality are not met and non-parametric statistical techniques must be used. This unit covers the most commonly used non-parametric statistical techniques. Chi-square compares two or more sets of nominal data that have been arranged into categories by frequency counts. Sex is an example of nominal data. Spearman's rank-order correlation coefficient determines the relationship between two sets of ordinal data. It is the non-parametric equivalent of Pearson's correlation coefficient. The Mann-Whitney U-test is used to determine the significance of the difference between rankings of two groups who have been ranked on the same variable. It is the non-parametric equivalent of an independent, two-group t-test. Kruskal-Wallis ANOVA by ranks compares the ranking of three or more independent groups. It is similar to a simple ANOVA. Friedman's two-way ANOVA by ranks determines the significance of the difference between ranks on the same subjects. It is similar to repeated measures ANOVA.
Now let's start chi-square with a test for goodness of fit. Now the chi-square test for goodness of fit tests claims about population proportions. It is a non-parametric test that is performed on categorical data, that is data that is on the nominal or ordinal scale. So let's work with an example. In the 2000 U.S. Census, the ages of individuals in a small town were found to be the following. We found out that 20% of the people were less than 18 years old, 30% were between 18 and 35, and 50% were greater than 35. So those are our population proportions. That's the distribution of ages we would expect to find in any given sample. Now, in 2010, the ages of 500 individuals were sampled, and below are the results. We have 121 people who are less than 18, 288 that are between 18 and 35, and 91 that are greater than 35. Using alpha 0.05, would you conclude that the population distribution of ages has changed in the last 10 years? So, we have our expected probabilities, and we have our actual observed values here. So based on these expected values, if we took a sample of 500, what would you expect the observed values to be? Well, if you expected 20% of those 500 people to be less than 18, you'd expect 100 to be less than 18. You'd expect 150 to be between 18 and 35, and you'd expect 250 to be greater than 35. So now we have what actually occurred in our sample of 500 and what we would have expected to have occurred in our sample of 500. And now we can do our hypothesis tests for chi-square test for goodness of fit, starting with defining the null and alternative hypotheses. Our null is that our data meet the expected distribution, and the alternative is that the data do not meet the expected distribution. Alpha is going to be 0.05, just like always. Calculating degrees of freedom is done like this. We just take the number of groups we have and subtract 1. Here we have 3 groups, 18, 18 to 35, and 35. So we just take 3 minus 1 and get 2 degrees of freedom. We then use that to find our decision rule. We have this chi-square table where we look up alpha 0.05 with 2 degrees of freedom, and we find 5.99147. So we say, if the chi-square we calculate is greater than 5.99, we're going to reject the null hypothesis. Calculating the test statistic for a chi-squared is actually not that bad. It follows this equation right here, where we take every observed minus expected, square it, divide by expected, and then add everything together. So it looks something like this. For less than 18, we observed 121 and we expected 100. So it's 121 minus 100 squared divided by 100. And then we add the other two observed minus expected fractions to get our total chi-squared, which in this case is 232.494. Which brings us to the result. Remember, we're going to reject the null if it was greater than 5.99, and it definitely was, 232. So we will reject the null hypothesis and say that the ages of the 2010 population are different than those expected based on the 2000 population. The sample that we observed was different than the sample we expected to find, using a chi-square test for goodness of fit. Now, in addition to the Pearson correlation, we also have the Spearman correlation. So far when I've talked about Pearson's R, I was talking about a correlation coefficient which measures the relationship between two continuous variables, that is, two variables that are either on the interval or ratio scale. Now, the Spearman correlation is used when you're measuring the relationship between two ordinal variables, or you're measuring the relationship between two variables that are related, but not in a linear fashion. Like, look at this right here. You can obviously see that whatever x is and whatever y is, there's some kind of relationship, but it's more curvilinear. It'd be more difficult to draw a line through that. But you also couldn't say there's no relationship because there obviously is one. So we would use something like the Spearman correlation to calculate that. So here is a sample data set. We've got some ordinal data here, 6 x's and 6 y's. Now, what we need to do with the Spearman correlation is we must first rank the scores. So I'm going to replace the score with what rank it has. The lowest score has the lowest rank, and the highest score has the highest rank. So 2, 5, 8, 11, 15, 16 turns into 1, 2, 3, 4, 5, 6. And the same for y. So now we're just going to forget about the original data, and we're just going to deal with these ranks. And we're going to calculate this R, which should look a lot like a regular R. Just now we have ranks instead of raw scores. So let's create our XY matrix, and let's start working through this. First, I'm going to find the sums of all of our columns. So the sum of all x is 21, sum of all y is 21, and the sum of all xy is 56. So let's get started with this. We can replace n with 6 because we know that there are 6 people in the entire analysis. And then we can put in 56, 21, and 21 because those are the sums that we already found out. We just need to find the bottom part of the fraction now. So we can put in the 21s there, and we need to find out the sum of all x squared and the sum of all y squared. So the sum of all x squared is each individual x squared and then added together. And the same for y. It's just each individual y squared and then added together. So both of those add up to be 91. And we can put 91s into the equation. So this is a little bit easier than a Pearson's R. These numbers are definitely easier to find. And now that we have this, we can work through it and solve for R, which, believe it or not, is negative 1.00. We have a perfect negative relationship, which should make sense looking at the x's and y, because every time x goes up 1, y goes down 1. That is a perfect negative relationship. So we're going to say that x and y have a strong negative relationship, whatever they are, strong negative relationship, using the Spearman correlation for ordinal data for ranked data. Another statistical test that probably isn't performed very often is a Mann-Whitney U. Now, the Mann-Whitney U is a version of the independent samples t-test that you perform on ordinal or ranked data. So now instead of continuous data, we have ordinal data. So here's some ordinal data displayed in a table. Is there a difference between treatment A and treatment B using an alpha level of 0.05. We can perform hypothesis testing on this just like any other test. And that starts with defining our null and alternative hypotheses. Now, it's going to be pretty similar to an independent samples t-test. Our null hypothesis is that there's no difference between the ranks of the two treatments, and the alternative hypothesis is that there is a difference between the ranks of the two treatments. Our alpha level, like I said, is just going to be 0.05. Now, our decision rule. So the Mann-Whitney U follows a z-distribution when your sample size is greater than 20. Now, you may have noticed that my sample size was not greater than 20. We're still going to use the z-distribution because I want to show you how it works. The reason I have such a small sample is because I'm trying to keep the example simple so it's easier to understand. Just realize that if you're doing a Mann-Whitney U using the z-distribution, you're going to want to have a sample size of at least 20. So using this z-table to find our decision rule, remember we have an alpha level of 0.05, and this is a two-tailed test, just like an independent samples t-test, right? We're testing to see if A and B are different. So that means the area in the body is going to be 0.9750, and our z will be 1.96. That should be review. If it's not, you can go back to one of the earlier lectures on z-scores to figure out just what I'm doing here. But that's our z. So if our z is less than negative 1.96 or greater than positive 1.96, we're going to reject the null hypothesis. So let's start calculating the test statistic. I'm going to move the table like that so it's easier to see. So what we're going to need to do is rank the data. We have 12 scores here, so we're going to rank them from 1 to 12. And that's what we do. We rank them from lowest to highest, and we also indicate which sample they came from. Now you may notice right here we have two 19s. So how do you rank two 19s? I mean, if they're the same number, how do you rank them? Well, in order to do that, you actually average the ranks. So instead of 4 and 5, they would now both be 4.5, right? That's just 4 plus 5 divided by 2 is 4.5. So now they're both ranked 4.5. Now next, you are going to assign points. So here's how that works. For every B sample, it will get 1 point for every A sample that is above it. Now every B has 6 A's above it, so they get 6 points. Now every A gets a point for every B that's above it. There are no B's above A's, so those all get zeros. Good? So we have our table with our ranks, scores, samples, and points. So we're going to calculate U of A and U of B. Those are just found by adding together all the points for A and all the points for B. So we get 0 and 36. Now we're doing this to find a U. U is the smaller of those two values. The smaller of those two values is 0. We have 0 and 36, so we're going to choose 0 to be our U. Usually the lower the U is, that means the more different your groups are. So you can expect that these two groups are very different, but let's keep doing the test and we'll see what happens. Now our U is 0, and we have this equation to calculate Z. And really that's pretty easy. We know the U is 0, we know that there are 6 A's and 6 B's, so we just put all that stuff in there that we already know, and we find a Z of negative 2.88. So now we can go to the next step, which is stating our results. Remember that our decision rule was that if Z is less than negative 1.96 or greater than positive 1.96, we can reject the null. And here we got a Z of negative 2.88, so we can reject the null hypothesis and conclude that there is a difference between the ranks of the two treatments, as found using a Mann-Whitney U.
In this lecture, we're going to perform a Kruskal-Wallis test. The Kruskal-Wallis test is a version of the independent measures, or one-way ANOVA, that can be performed on ordinal or ranked data. Ordinal data is displayed in the table below. Here we have 3 groups, and we have 6 scores for each group. Is there a difference between groups 1, 2, and 3 using an alpha level of 0.05? We're going to perform a Kruskal-Wallis test on this data set to see if there's a difference between the 3 groups. Our Kruskal-Wallis test has 7 steps. First, we're going to define what our null and alternative hypotheses are. Next, we're going to state our alpha. Then we're going to calculate our degrees of freedom. then we state our decision rule, then we actually calculate the test statistic, and then finally we state our results and our conclusion. So let's start with step 1, defining the null and alternative hypotheses. For a Kruskal-Wallis test, our null hypothesis, H0, is that there is no difference between the treatments that we're comparing. Our alternative hypothesis, H1, is that there is a difference between the treatments that we are comparing. Step 2 is to state the alpha level. That's easy because I already said use an alpha level of 0.05. Next, we're going to calculate our degrees of freedom. Degrees of freedom are equal to k minus 1, where k is the number of groups you have. So, in this case, our degrees of freedom is equal to 3 minus 1, or 2. Next, based on that information, we state our decision rule. Here we go to our chi-square table, which is what we use for a Kruskal-Wallis test. We have an alpha level of 0.05 and 2 degrees of freedom. Using that information, we can find our critical value. Here, our critical value is 5.99147. So, if the chi-square value that we calculate is greater than 5.99, we can reject the null hypothesis and say that there is a difference somewhere between the three groups. If chi-square is not greater than 5.99, then we will not reject the null hypothesis. Now let's actually calculate our test statistic. Here we have our information. I just moved it over to the left so we can work with it. And what we want to do for a Kruskal-Wallis test is organize our scores by rank. So basically we want to organize them from smallest to largest. Here we have 3 groups with 6 scores in each group, so we have 18 scores. We're going to rank those 18 scores so we can calculate the chi-square statistic for our Kruskal-Wallis test. Here we just taken the original scores and ranked them. For example, our smallest score is 2, so that's rank 1, while our largest score is 36, so that's rank 18. So now I've changed the table to reflect that. We're no longer working with the original data, we're working with our ranks, because remember, our original data is ordinal. So now we have our table with our ranks. So now we can calculate our test statistic. Our test statistic, we're going to call it H, but just basically think of it as a chi-square value. And here we have our equation for calculating that. It's this kind of complicated 12 divided by n times n plus 1 times all of the sum squared divided by n minus 3 times n plus 1. That sounds kind of confusing, but I'll show you right now how we actually get those numbers. So first, our t is our sums. So for example, the sum of group 1 is 39, the sum of group 2 is 65, the sum of group 3 is 67, and our n is just our sample sizes. We have 6 scores in each of our groups in each of our samples, so all of our n's are 6. So now that we have that, we can just plug those into the equation to solve for h. For each t square, t1, 39, t2, 65, t3 is 67. Our big N reflects our total sample size, so while each small n is 6, our total sample is 18. It's just 6 plus 6 plus 6. And we just plug all of those values into the equation to find our h value of 2.854. So now we can move on to our results. Remember, our decision rule was if our chi-square value was greater than 5.99, we were going to reject the null hypothesis. In this case, our value is 2.854. Because it's not greater than 5.99, we do not reject the null hypothesis. Now we state our conclusion. Basically what that means is that there is no significant difference among the 3 groups that we compared in this Kruskal-Wallis test.
Another kind of non-parametric test is the Friedman test. The Friedman test is a version of the repeated measures ANOVA that can be performed on ordinal, that is ranked, data. So here's some ordinal data displayed in a table. Is there any difference between weeks 1, 2, and 3 using alpha 0.05? Now remember, this is kind of like repeated measures ANOVA. because here we have 6 subjects and we're measuring them 3 times, week 1, week 2, and week 3. So let's do a hypothesis test for the Friedman test using the same 7 steps that we usually do. Step 1, which is to state our null and alternative hypotheses. So our null is that there is no difference between the 3 conditions, and our alternative is that there is a difference somewhere between the 3 conditions. Our alpha, like I said, is just going to be alpha equals 0.05. For our degrees of freedom, we're going to use degrees of freedom equals k minus 1. K is the number of groups we're comparing. Here we have 3 groups, so 3 minus 1 is 2. Our analysis will use 2 degrees of freedom. And now we'll use those degrees of freedom to find our decision rule. Now this is going to follow the chi-square distribution. So looking at this chi-square table, with an alpha level of 0.05 and 2 degrees of freedom, we find a critical value of 5.99147. That means that if we calculate a chi-square value greater than 5.99, we're going to reject the null hypothesis. Next, we will actually calculate that value, which is our test statistic. So here's our data. I just moved it over a little bit, and now I'm going to duplicate it so I can show you something. These scores that I have indicated in red, 27, 20, and 34, remember, those all come from the same person at week 1, week 2, and week 3. What you need to do is rank those scores within the row, like this. So for example, 27 is the second highest score, 20 is the lowest score, and 34 is the highest score. So we put in 2, 1, 3 to rank that person based on all of their other scores. And we're going to do that for all 6 subjects. And now we can throw away the original data and just use these new ranks that we've calculated. Now we need to find the rank for each of the columns. So the total rank for week 1 is 9, the total rank for week 2 is 14, and the total rank for week 3 is 13. And we're going to use these 3 r's in our chi-square equation, which is pretty easy because we know that n is 6, we know that k is 3. We just need to solve for the sum of all r squared, which looks something like that. The sum of all y squared is just 9 squared plus 13 squared plus 14 squared. And then we put in n and k, and suddenly the equation is pretty easy to figure out. You just put that in a calculator and you find out that chi squared equals 2.33. So to our results, remember we were going to reject if chi squared was greater than 5.99, and our chi squared was 2.33. So we will not reject the null hypothesis. We can conclude that there is no difference among the 3 groups using a Friedman test.
Let's review.